Imagine that this moment, the one you are experiencing right now, is not passing. It is not slipping into the past, and it is not arriving from the future. It is simply there, fixed, permanent, woven into the structure of reality alongside every other moment that has ever existed or ever will. Your birth is still happening. Your last breath is already complete. The light from a star that exploded 10 billion years ago is still traveling, and at the same time, has already arrived. This is not science fiction. It is one of the most serious propositions in modern physics, and it carries a name: Eternalism. The question is direct. What would happen if every moment in time existed simultaneously, not as a memory, not as a prediction, but as an equally real and permanent feature of the universe? The consequences are stranger than most people realize. Albert Einstein implied it. Hermann Minkowski formalized it. The mathematics of relativity demands something very close to it, and yet our daily experience tells us the opposite. We feel time pass, we watch coffee cool, we grow older, we remember yesterday and anticipate tomorrow. So, which is correct? The lived sensation of flowing time, or the equations that describe a universe where time does not flow at all? Over the course of this investigation, we will examine the physics, the philosophy, and the deep implications of a reality in which the past is not gone and the future is not waiting. We will look at what light cones reveal, what quantum mechanics complicates, and what consciousness might mean inside a frozen cosmos. The conclusions will challenge the most basic assumption you have ever made, which is that time moves. Picture a long river seen from above. The water appears to flow, carrying leaves and sediment from its source to its mouth. Now imagine that the river is not water at all, but ice. The shape is the same. The bends, the eddies, the rapids are all preserved, but nothing moves. Every leaf is fixed in its position. Every sediment particle is locked in place. From a single point along the surface, you cannot tell the difference between a flowing river and a frozen one if you are looking only at a single instant. The flow is something inferred, something added by the observer, not something necessarily present in the structure itself. This is the central image that physicists invoke when they describe what is sometimes called the block universe, a model in which time is not a current carrying events forward, but a dimension along which events are arranged, complete, and unchanging. To grasp why this picture has gained such traction among professional physicists, it helps to understand what the older picture, the one most of us hold instinctively, actually claims. In the intuitive view, there is a moving present moment, a kind of cosmic spotlight that illuminates one slice of reality at a time. The past has been illuminated and is now gone. The future has not yet been illuminated and does not yet exist. Only the present is real. This view is sometimes called presentism, and it matches the way we live. We make plans for a future that feels open. We mourn a past that feels lost. We act in a present that feels uniquely substantial. Reality in this picture is constantly being renewed, constantly coming into existence, constantly slipping away. Time is doing something. Time is happening. But there is a problem with this picture, and it appeared more than a century ago when a young patent clerk in Bern began to wonder what the world would look like if you could ride alongside a beam of light. The patent clerk was Einstein. The wondering became special relativity, and the consequences for the concept of time were severe enough that physicists have been grappling with them ever since. The trouble is not that Einstein discovered time was slower or faster than expected. The trouble is that he discovered there is no universal answer to the question of when. Two events that one observer judges to happen at the same moment can, for another observer moving at a different velocity, occur at different moments, and there is no experiment that can decide which observer is correct. Both are. The notion of a single shared present, a single now that stretches across the cosmos, simply does not survive contact with the physics of moving frames of reference. This is not a quirk of fast travel or laboratory exotica. It is a feature of the world we inhabit every day. The effects are small at the speeds we normally encounter, but they are real and they are measured. Atomic clocks aboard aircraft tick at slightly different rates than identical clocks on the ground. The global positioning system would fail within minutes if it did not compensate for relativistic time dilation. Particles produced in cosmic ray showers in the upper atmosphere live just long enough to reach the ground because, from their perspective, time is passing more slowly. These are not theoretical curiosities, they are engineering facts, and they all point to the same conclusion. Time is not a universal flow. Time is local. Time depends on the observer. Time is something more like a coordinate than a current. Once you accept that there is no universal now, the entire structure of common sense begins to tremble. If your now and my now can disagree, then what is real for you and what is real for me must also disagree, unless we are willing to say that reality itself is observer, dependent in a very strong sense, or unless we are willing to say that the past and the future are just as real as the present, and that what each of us calls now is merely a slice through a larger structure that contains them all. Most physicists, when pressed, choose the second option. They do this because the first option, the idea that reality itself flickers in and out of existence depending on who is looking, seems even stranger than the alternative. So they accept the block. They accept that the universe is a four-dimensional object, 3 dimensions of space and 1 of time, and that all of its contents, from the first moment of cosmic expansion to whatever lies at the far end of cosmological history, exist together as a single structure. What does this mean for everyday experience? Consider the smell of bread from a bakery you walked past as a child. In the presentist picture, that smell is gone. The molecules dispersed, the bakery may no longer exist. The child you were has been replaced by the adult you are. Nothing remains except your memory, which is a pattern of neural connections in the brain you have today. But in the eternalist picture, the smell is not gone. The molecules are still there, in the past, suspended in the four-dimensional structure of the universe. The child you were is still standing on that street. The bakery is still open. The afternoon light is still slanting through the window. None of it has been erased because erasure would require the past to be a region where things used to be and are no longer. And in the block universe, there is no such region. The past is simply elsewhere along the time dimension, in the same way that another continent is elsewhere along a space dimension. You cannot reach it from where you stand, but its inaccessibility does not imply its non-existence. This is a peculiar kind of consolation, and also a peculiar kind of strangeness. It suggests that nothing is ever truly lost, but it also suggests that nothing is ever truly created. Every event is already there, already complete, already part of the structure. The poem you have not yet written is, in some sense, already finished, sitting at a coordinate in space-time you will eventually reach. The conversation you will have tomorrow has already happened, from the perspective of someone who could see the entire block from outside. There is something dizzying about this, and there's also something orderly. The universe stops being a place where things come and go and becomes a place where things simply are, arranged across 4 dimensions like the contents of a vast, silent gallery. Of course, this is a model. It is a way of describing what relativity seems to imply, and it has competitors. Some physicists and philosophers argue for a growing block, in which the past and the present are real, but the future is not, with the structure expanding moment by moment as new slices are added. Others argue for a presentism that can somehow be made compatible with relativity, though the technical difficulties are formidable. Still others argue that the question is malformed, that we are asking metaphysical questions of mathematical structures and expecting unambiguous answers where none are available. All of these positions have serious defenders, none of them are settled. But the block universe, the eternalist picture, has the virtue of being the simplest interpretation of what the equations actually say, and that simplicity has earned it a central place in the conversation. It is worth pausing here to consider how strange it is that a question about the nature of time should have been transformed in the span of a single human lifetime from a matter of pure philosophy into a matter of physical theory. For most of recorded history, the flow of time was taken for granted. It was the medium in which everything happened. To ask whether it really flowed would have seemed as pointless as asking whether space really extended. But the physics of the 20th century changed that. It made time a variable, a coordinate, a thing that could be measured differently by different observers, a thing whose universality could no longer be assumed. And once that happened, the old certainties dissolved. The river became, at least possibly, a frozen one. And the question of what we are actually living inside became open in a way it had not been before. To make sense of how we got here and of what the eternalist picture demands of us, we have to go back to the moment when the old picture first cracked. We have to follow the trail of a letter written by an aging physicist to the family of a friend, in which he made a claim about time that has unsettled thinkers ever since. Hermann Minkowski was a German mathematician who taught Einstein at the Zurich Polytechnic and remembered him with a certain amused condescension as a lazy student. When the young Einstein began publishing the papers that would transform physics, Minkowski was at first dismissive. He could not quite believe that the indifferent pupil he recalled was the same person now reshaping mechanics, but he read the work carefully, and he saw something in it that even Einstein had not yet articulated clearly. He saw that the equations of special relativity were not merely a set of rules for translating measurements between observers. They were the equations of a geometry, a four-dimensional geometry in which space and time were not separate stages on which physics played out, but coordinates in a single unified structure. In 1908, Minkowski gave a lecture in Cologne that has become one of the most quoted in the history of physics. He told his audience that henceforth space by itself and time by itself were doomed to fade away into mere shadows, and that only a kind of union of the two would preserve an independent reality. The phrasing was deliberately grand. Minkowski knew he was announcing something. He was telling the assembled physicists that the world they thought they lived in, a three-dimensional world that endured through time, was not quite right. The world they actually lived in was four-dimensional, and the apparent separation of space and time was an artifact of how observers happened to move through it. To see what Minkowski meant, it helps to think about how we already use geometry to describe space. A point on a map can be specified by two coordinates, longitude and latitude. If you want to talk about a point in a building, you add a third coordinate, height, 3 numbers, and you have located a point in space. Now add a fourth number, the time at which something happens at that location, and you have specified an event. The fourth number is just as much a coordinate as the other 3. It is not a measure of how the location is changing. It is part of the address of a particular happening. Minkowski's insight was that this fourth coordinate could be treated mathematically on the same footing as the other 3, with one important difference. The geometry of the four-dimensional structure was not quite the same as the geometry of ordinary three-dimensional space. The way distances were measured involved a minus sign where one might naively expect a plus sign. This sign difference is small in appearance, but enormous in consequence. It is what distinguishes time from space within the unified structure. It is what ensures that you can move freely in space, but only in one direction in time. And it is what gives the geometry its distinctive character. In ordinary space, the distance between 2 points is found by squaring the differences in each coordinate, adding them, and taking the square root. This is the Pythagorean theorem extended to 3 dimensions. In Minkowski's four-dimensional spacetime, the equivalent quantity, called the interval, is found by squaring the differences in the spatial coordinates, subtracting the squared difference in time, multiplied by a constant related to the speed of light, and taking the square root of whatever is left. The subtraction is the key. It means that 2 events separated by both space and time can have an interval that is positive, negative, or 0. Each case has a physical meaning. A positive interval, called spacelike, means that no signal could ever travel from one event to the other without exceeding the speed of light. A negative interval, called timelike, means that an object moving slower than light could travel between them. A 0 interval, called light-like or null, means that a beam of light, and only a beam of light, could connect them. This classification, which sounds technical, has profound implications. It means that the four-dimensional structure of spacetime is not a featureless block in which any event can influence any other. It is a structure with a definite causal architecture. Some events are accessible from a given starting point, others are not. The structure determines what can affect what, and it does so in a way that does not depend on the observer. Two observers moving relative to each other may disagree about which of two events occurred first, if those events are separated by a space-like interval, because in that case, there is no causal connection between them, and the order is genuinely a matter of perspective. But they will always agree about the order of two events separated by a timelike interval, because there the order corresponds to the direction along which a physical object or signal can actually travel. The geometry guarantees consistency where consistency is required, and it permits flexibility where flexibility is harmless. Minkowski's diagram, the visual representation of this geometry, has become a standard tool. It plots time on the vertical axis and one or more dimensions of space on the horizontal axis. An object at rest traces a vertical line, called its world line, ascending through time without changing position. An object moving at constant velocity traces a tilted line, the tilt indicating its speed. An accelerating object traces a curved world line. A beam of light moving at the maximum possible speed traces a line at 45 degrees, the steepest tilt the geometry allows. The collection of all possible world lines for light passing through a given event forms a structure called the light cone, which we will examine more closely in a moment. But the essential point about the diagram is that it represents not a moving picture, but a fixed map. Every event is plotted at a definite coordinate. Every world line is drawn in its entirety. There is no animation, there is no time slider. The diagram shows the universe as a single object, complete from beginning to end, with motion represented by the shape of curves rather than by any actual movement on the page. This is the visual heart of the block universe. When physicists draw a Minkowski diagram, they are not depicting a snapshot of the universe at one moment. They are depicting the universe itself, with all of its moments laid out as a geometric pattern. The fact that world lines have shapes, that they tilt and curve and intersect, is not a metaphor. It is the literal content of the theory. The world is four-dimensional. The shapes are the histories. And the histories are not unfolding. They are simply there, drawn into the structure once and for all. This way of thinking has a particular elegance, and it also has a particular discomfort. The elegance is that it eliminates a number of conceptual problems that plague the older picture. There's no longer any need to explain how the present moment moves, because there is no moving present. There is no need to ask where the past goes when it ceases to be present, because the past does not cease to be anything. It simply occupies a region of spacetime that lies in the direction we conventionally call earlier. The asymmetry between past and future, the felt difference between memory and anticipation, becomes a question about the structure of the world lines we are riding on, not a question about the metaphysics of time itself. The discomfort is that this elegance comes at a cost. The cost is intuition. The cost is the conviction, deeply held by almost everyone, that things actually happen, that the present really is special, that the future really is open. Minkowski's geometry does not accommodate that conviction. It treats it as a feature of consciousness rather than a feature of the world. It is worth dwelling on what kind of object Minkowski was describing. A four-dimensional manifold is not something we can visualize directly. Human beings evolved to perceive three spatial dimensions, and our visual cortex has no native representation for a fourth. When we try to picture spacetime, we typically resort to projections. We draw two spatial dimensions and one time dimension, suppressing the third spatial dimension because there is no way to put it on the page. We talk about slicing the four-dimensional structure into three-dimensional snapshots, the way you might slice a loaf of bread into pieces, even though the structure itself does not come with any preferred way of being sliced. Different observers slice it differently depending on their motion. The slices are not features of the loaf. They are features of how the loaf is being cut. The loaf in itself is just the loaf. This metaphor of the loaf is sometimes called the block universe loaf, and it captures something essential about the eternalist picture. The loaf exists all at once. The slices are mental, or at least observational. The crust at one end of the loaf corresponds to what we might call the beginning of time, and the crust at the other end corresponds to whatever lies at the far end of cosmological history. The interior of the loaf is filled with the world lines of every particle, every star, every conscious being, every event. None of these world lines are moving. They are simply shapes within the loaf, defined by their relationships to one another. The fact that we experience ourselves as advancing along our own world lines, encountering new events as we go, is a feature of our experience, not a feature of the loaf. The loaf does not advance. The loaf simply is. Minkowski died in 1909, less than a year after his Cologne lecture, of complications from appendicitis. He did not live to see the full elaboration of his ideas. Einstein, who had been ambivalent about the geometric formulation at first, came to embrace it and to extend it. The general theory of relativity, which Einstein completed in 1915, takes Minkowski's flat four-dimensional spacetime and adds curvature. Gravity, in general relativity, is no longer a force pulling objects toward one another. It is a feature of the geometry of spacetime, a bending of the four-dimensional structure caused by the presence of mass and energy. World lines that appear curved when we describe them in three-dimensional language are actually as straight as they can be, given the curved geometry through which they pass. The block becomes a block that is bent, dimpled, warped by the matter it contains. But it is still a block. The whole structure still exists as a single object. The geometry has become more interesting, but the picture has not fundamentally changed. What this means for the question of all moments existing simultaneously is significant. If the universe is a four-dimensional manifold, possibly curved, possibly closed, possibly extending in ways we have not yet mapped, then asking whether all moments exist together is asking whether the manifold itself exists as a whole. And the answer, given by the mathematics, is yes. The manifold is a single object. Its parts are not appearing and disappearing. They are all there, related by the geometry, woven into a structure that does not require time to bring it into being because time is one of its dimensions. But this raises a question that the geometry does not answer on its own. If all moments exist together, what becomes of the present? What becomes of the now that each of us insists is special, the slice of reality that we are actually inhabiting right at this instant? The geometry does not seem to single out any slice as special. It treats them all symmetrically. And yet here we are, each of us aware of one slice and not the others. The relationship between the four-dimensional structure and the felt present is a problem that the mathematics alone cannot solve. The disappearance of the universal present is one of the strangest consequences of taking relativity seriously, and it is also one of the most resisted. People can accept that clocks run at different rates. They can accept that lengths contract in the direction of motion. They can accept, with some effort, that simultaneity is relative. But they balk at the conclusion that follows from all of this together, which is that the now they are experiencing right at this moment has no special status in the structure of the universe. It is not the leading edge of reality. It is not the place where existence is happening. It is just one slice of the four-dimensional block, no more real and no less real than any other slice. To understand why this conclusion is so difficult to accept, consider what we mean when we say that now is special. We mean that now is when things are happening. We mean that the past, whatever it was, is no longer occurring, and that the future, whatever it will be, is not yet occurring. The present, by contrast, is the place where action takes place. It is where coffee gets cold, where decisions get made, where light enters our eyes and reaches our retinas. The present is, in this view, the unique location of reality. And it moves. The moment that was present a second ago is no longer present. The moment that will be present a second from now is not yet present. The present is a kind of advancing front, sweeping through the universe and converting potential events into actual ones, and then converting actual events into the dead matter of the past. This is a coherent picture, and it is the picture almost everyone holds intuitively. The problem is that it cannot be reconciled with relativity. The advancing front, the moving present, would have to be a feature of the universe that all observers could agree on. It would have to specify at any given moment which events are happening right now and which are not. But relativity tells us that no such specification is possible. The events that are happening right now for an observer at rest are different from the events that are happening right now for an observer moving rapidly past them, and there is no experiment that can determine which observer's now is the real one. Both observers are equally entitled to their definition of the present, and if both are entitled, then there is no single present that the universe possesses. There are only the presents that observers construct from their particular vantage points. Some philosophers have tried to rescue the moving present by arguing that even if observers disagree about which events are simultaneous, there might still be a privileged frame of reference, some absolute rest frame that defines the true present. The events that are simultaneous in this privileged frame would be the real present, and the disagreements among other observers would be merely apparent. The cosmic microwave background, the residual radiation from the early universe, does in fact define a kind of preferred frame for observational purposes. It is the frame in which the radiation looks the same in every direction. Observers moving relative to this frame see the radiation slightly blue-shifted in front of them and slightly red-shifted behind them, and they can measure their motion relative to it. So there is, in a certain operational sense, a cosmic rest frame. But this does not solve the philosophical problem. The cosmic microwave background does pick out a frame that is convenient for cosmology, but it does not pick out a frame that is metaphysically privileged in the way the moving present would require. The laws of physics work the same in all inertial frames. The mathematical structure of relativity does not single out the cosmic rest frame as the home of the true now. To claim that it does would be to add a piece of structure to physics that the equations do not contain, and that no experiment has detected. It would be to insist on philosophical grounds that one of the many possible slices of the block universe is the real one, even though the physics treats them all alike. This is a coherent position, but it is not a position that the physics supports. It is a position that the physics tolerates only because the physics is silent on the question. So we are left with a peculiar situation. The mathematics describes a four-dimensional structure in which no slice is privileged. The experience describes a moving present that feels unmistakably special. And there's no obvious way to bridge the two. The eternalist response is to say that the experience is misleading. The moving present is something the mind constructs, not something the universe contains. The feeling that now is special is a feature of how consciousness operates, not a feature of the underlying reality. This is a strong claim, and it has consequences. If the moving present is an illusion, then so is the sense of becoming, the sense that things are coming into existence and passing away. The universe, in this view, is not a place where things happen. It is a place where things are. Events do not occur. They merely exist at their assigned coordinates in the four-dimensional structure. There is something deeply counterintuitive about this, and there is also something liberating about it, depending on which side of the temperament you happen to be on. The counterintuitive part is obvious. It seems to deny the most basic fact of human experience, which is that things change. The liberating part is less obvious but worth examining. If nothing is ever truly lost, if every moment exists permanently in the structure of the universe, then the past has a kind of persistence that the presentist picture denies it. The people you have loved who are no longer with you in the moving present are still with you in the only sense that anyone is ever with anyone in the four-dimensional structure. They exist at their coordinates. Their world lines are part of the block. The fact that your own world line has moved beyond theirs does not erase them. It just means you are no longer at the same place in space-time. This is, of course, cold comfort if what you want is to actually see the people you have lost. The eternalist picture does not allow you to revisit them. You cannot travel back along your world line. You cannot reach into another slice of the block. The structure is fixed, and your position within it is determined by the geometry. You are where you are, and they are where they are, and the separation between your coordinates is not something you can cross. But the picture does insist that the separation is not annihilation. The past is not gone in the sense of having been erased. It is gone in the sense of being elsewhere, and there is a real difference between those two kinds of absence. The same logic applies to the future, with consequences that may be even more unsettling. If the future already exists in the block, then everything that will happen to you has, in some sense, already happened. Your future joys, your future losses, your future decisions, your final moment are all there at their coordinates, complete and determinate. You will reach them in due course, following the curve of your world line through the four-dimensional structure. But they are not waiting to happen. They are already happening, or have already happened, depending on how you want to phrase it. The slicing into past, present, and future is, again, a feature of your particular position in the block, not a feature of the block itself. The disappearance of the special present has been a focus of philosophical debate for decades, and it has divided thinkers into two main camps. On one side are the Eternalists, who accept the implications of relativity and conclude that all moments are equally real. On the other side are the Presentists, who insist that only the present exists and that the moving now is a fundamental feature of reality. There's also a middle position, sometimes called the growing block, which holds that the past and the present are real, but the future is not. The growing block tries to preserve some of the intuition of becoming, the sense that new moments are being added to reality, while accepting the relativistic constraint that the past cannot be erased. But the growing block has its own difficulties, including the question of where, exactly, the leading edge is and whether it can be defined in a relativistically invariant way. The debate is not merely academic. It touches on questions of profound human importance. If only the present is real, then mortality has a particular character. The dead are truly gone. The unborn are truly absent. Reality is a thin sliver of advancing now, and everything outside it has either ceased to be or has not yet come into being. If all moments are real, then the picture changes. The dead are not gone, only elsewhere. The unborn are not absent, only at coordinates we have not yet reached. The universe contains all of its inhabitants at once, even if no inhabitant can perceive more than one slice at a time. These are not equivalent pictures. They feel different. They have different implications for grief, for hope, for the meaning of action. And the question of which one is true, or whether either of them is the right way to frame the question at all, is one that physics has opened up without being able to definitively close. What physics has done is shift the burden of proof. Before relativity, the moving present was the default assumption. The block universe would have seemed like an extravagant metaphysical claim. After relativity, the situation reversed. The block universe became the simpler interpretation of the equations, and the moving present became the claim that required extra justification. This is not a matter of consensus among physicists, many of whom are professionally agnostic about metaphysical questions of this kind. It is a matter of what the equations most naturally suggest. They suggest a structure in which no slice is special. They suggest a universe in which time is a dimension, not a flow. They suggest that the now you are inhabiting is one of many, and that the others are no less real for being inaccessible to you. But all of this discussion of slices and presents has been carried out at a relatively informal level. To see exactly what the equations are doing and exactly what kind of structure they describe, we need to look more closely at the geometric object that organizes the entire causal structure of spacetime. We need to look at the light cone. Imagine you are standing at a single point in spacetime, an event marked by your present location at this exact instant. From this event, light travels outward in every direction at the same finite speed. After 1 second, the light has formed an expanding sphere around you with a radius of roughly 300,000 kilometers. After 2 seconds, the sphere is twice that size. After 1 year, the sphere reaches out to a distance of 1 light year. The expansion continues indefinitely, traced through the structure of the four-dimensional universe. If you plot this expansion on a Minkowski diagram, with time running vertically and 1 or 2 spatial dimensions running horizontally, the expanding sphere of light traces out a cone. The point of the cone is the event where you are standing right now. The cone opens upward into the future, growing wider as time advances. This is your future light cone. There is a corresponding cone that opens downward into the past, representing all the light that could have reached you from earlier events. The two cones together, joined at the apex, form an hourglass shape centered on your present location. This double cone is called the light cone, and it is one of the most important structures in all of physics. It defines, with mathematical precision, which events in the universe can possibly affect you and which events you can possibly affect. Inside the future light cone are all the events you could potentially influence by sending out signals or by moving through space at less than the speed of light. Inside the past light cone are all the events that could have potentially influenced you by sending signals or by moving toward you at less than the speed of light. Outside, both cones lie events that are causally disconnected from your present moment. These are events that are too far away in space, given how little time has elapsed for any signal to have traveled between you and them. You cannot affect them. They cannot affect you. They are, in the strictest physical sense, elsewhere. This region outside the light cone is called the absolute elsewhere. It is a peculiar concept because it includes events that are happening right now in the conventional sense, events that some observer somewhere would say are simultaneous with your present moment. But because no signal can travel faster than light, no information about these events can reach you, and no action of yours can reach them. They exist in the eternalist picture, but they exist in a region of spacetime that is forever cut off from yours. The relativity of simultaneity, which we examined earlier, takes its full force here. The events in the absolute elsewhere can be called simultaneous with your present by some observers and not simultaneous by others, and the disagreement has no resolution because there is no causal connection that could be used to settle it. The light cone structure has consequences that ripple through every part of physics. It is the reason why causes always precede their effects in any consistent way. It is the reason why information cannot travel faster than light, since faster than light signals would carry events outside their light cones and create paradoxes. It is the reason why the geometry of spacetime is not arbitrary, but obeys strict causal rules. And it is the reason why the four-dimensional structure has a definite shape with regions that are timelike, spacelike, and light-like clearly distinguished from one another. The light cone is not a metaphor. It is the actual geometric object that organizes the causal architecture of the universe. For an observer at any point in space-time, the past light cone defines the set of events from which the observer could have received information. Every photon that has ever entered your eyes traveled along the surface of your past light cone. The stars you see at night, the sunlight that reaches you during the day, the photons bouncing off the page or screen in front of you, all of them have followed the light-like paths that converge on your present moment from the past. When you look up at the night sky, you are looking down the surface of your past light cone, seeing events that happened years, centuries, millennia, or millions of years ago, depending on how far away they were. The image of a distant galaxy is an image of the galaxy as it existed when the light left it, not as it exists now. In the eternalist picture, this is not just a quirk of light travel. It is a feature of how world lines are arranged in the four-dimensional structure. The galaxy as it was when the light left it is still there, at its coordinates in the block, just as the galaxy as it is now is also there, at different coordinates. Both versions exist. You can only see one of them, but the other has not vanished. It is simply elsewhere in the block. This raises an interesting question. If all moments exist in the block, and if light from the past is reaching us right now, then in what sense is the present special at all? The light cone gives us a way to formalize the answer. Your present moment is special for you, because it is the apex of your light cones. It is the point from which your past and future are organized. It is the coordinate at which your world line is, in a sense, anchored to the geometry. Every other observer has their own light cones anchored at their own coordinates. There are as many light cones as there are events. Each one is a structure within the block, defining a local notion of past and future. The block contains all of them. None of them is the master structure that organizes the others. In the eternalist picture, then, the moving present is replaced by a static geometry in which every event has its own light cone, and the experience of moving through time is the experience of being a world line that passes through a sequence of light cones, each one centered on a different event along the world line's path. As you move through space-time, the contents of your light cone change. Events that were in your future enter your past. Events that were outside your light cone, in the absolute elsewhere, never enter at all. The structure is fixed, but your position within it is constantly shifting in the sense that different points along your world line correspond to different vantage points. The shifting is not motion in the ordinary sense. It is more like the way the contents of a book change as you read through its pages. The book does not move. You move through it. And as you do, different content becomes accessible to you. This analogy, the book and the reader, is one that eternalists sometimes use. The book is the block. The reader is a world line. The pages are events. The reader experiences the book as a sequence because that is how reading works. But the book itself is not a sequence. It is a complete object. The first page exists at the same time as the last page, in the sense that both are part of the same book. The reader's experience of sequential reading is not a property of the book, but a property of the reading. If you could somehow look at the book from outside, you would see all the pages at once. You would see the entire story, not as a flow, but as a structure. The analogy is imperfect, because books are objects we can inspect from outside, while the block universe is something we are inside. We cannot step out of it to see it whole. We are confined to our own world lines, and our experience of space-time is necessarily local. But the analogy captures something important, which is that the structure can be complete and unchanging even while the experience within it is sequential and dynamic. The two are not in contradiction. They are talking about different things. The structure is the geometry. The experience is what happens when a conscious world line traverses a portion of the geometry. The light cone also gives us a way to think about what we can and cannot know. The events in your past light cone are events whose information has had a chance to reach you. They are, in principle, knowable. You can study them. You can investigate them. You can build instruments that detect the photons or particles that have traveled along the surface of your past light cone, and you can learn about the events that emitted those signals. The events outside your past light cone are not knowable in this way. They have not had time to send information to you. You can speculate about them, but you cannot directly observe them. The boundary of your past light cone is, in effect, the boundary of your possible knowledge of the universe. This boundary has expanded over the course of your life. When you were born, your past light cone was small because little time had passed for light to travel and reach you. As you grew older, the light cone expanded outward, encompassing more and more of the universe. Today, your past light cone reaches back to the moment of your birth and outward to a distance of decades in light years. You have, in principle, access to information from a substantial region of space-time. But there are limits. There are events in the early universe whose light has not yet reached you, and there are events at the far edges of the cosmos whose light may never reach you, given the expansion of space. The light cone is not infinite. It is bounded by the geometry of the universe and by the time that has elapsed. In the eternalist picture, the events outside your light cones do not cease to exist because you cannot see them. They are simply inaccessible. The four-dimensional structure contains them, but the structure does not deliver them to your world line. You are confined to a particular causal neighborhood, and the rest of the block is, for you, beyond reach. This is not a limitation of physics. It is a limitation of geometry. The light cone is the natural boundary of what any observer can ever know or affect, and it follows from the speed limit imposed by the constancy of the speed of light. The limit is not arbitrary. It is built into the structure of space-time itself. There is one more aspect of the light cone that deserves attention, and it concerns the question of whether the structure of space-time is purely deterministic. If all moments exist in the block, and if the light cones organize the causal relationships among them, then it might seem that the future is fixed in the same way that the past is fixed. The events in your future light cone, in this view, are already there, waiting for your world line to reach them. They are not being created as you advance. They are simply at coordinates you have not yet visited. This deterministic implication is one of the most contested aspects of the eternalist picture. and it raises questions about whether choice, agency, and possibility have any meaningful role to play in a universe where everything is already laid out. Some physicists and philosophers have argued that the eternalist picture does not actually require strict determinism. Quantum mechanics, which we will examine in due course, introduces an element of probability that complicates the simple block. Others have argued that even in a fully deterministic block, the experience of choice and the practice of decision-making remain meaningful, because the events along your world line include your decisions, and the decisions are real even if they are also fixed. These are deep questions, and they touch on some of the oldest debates in philosophy. For now, the point to hold on to is that the light cone structure is the geometric foundation that makes the eternalist picture coherent. Without the light cones, there would be no way to organize the causal relationships among events in a relativistically consistent way. With them, the four-dimensional structure becomes a definite object, with a definite architecture and with definite rules about what can connect to what. The light cones, then, are the scaffolding of the block universe. They are what gives it its causal coherence, and they are what makes the eternalist picture more than just a metaphysical claim. They make it a geometric necessity built into the equations that describe the world we actually inhabit. But geometry alone is not enough to answer every question about time. There are deeper puzzles about why time seems to flow in one direction even if it does not flow at all, that the geometry by itself cannot resolve. If the universe is a four-dimensional structure in which all moments exist together, there is a question that becomes immediately pressing. Why does time seem to have a direction? Why do we remember the past and not the future? Why does ice melt in warm water but never spontaneously reform from a glass of water at room temperature? Why do eggs scramble but never unscramble? The block universe, taken on its own, does not obviously contain any preferred direction along the time dimension. The geometry of spacetime treats earlier and later symmetrically. The equations of motion that govern the behavior of particles, whether we are talking about classical mechanics or quantum mechanics, are largely time symmetric. If you ran the equations backward, swapping the sign of the time coordinate, they would describe a world that is just as physically valid as the one we observe. And yet we never observe such a world. We observe a world in which time flows or appears to flow in one direction only. Where does this asymmetry come from, if not from the geometry itself? The answer that has emerged over the past century and a half is one of the great achievements of physics, and it has a peculiar status. It does not say that time itself has a direction. It says that the contents of the universe, the actual matter and energy and configurations of particles, are arranged in such a way that one direction along the time dimension looks very different from the other. The arrangement is statistical, not fundamental. It has to do with the way large numbers of particles can be organized and with the overwhelming likelihood that any given organization will evolve toward configurations that are more disordered rather than less. The technical name for this is the second law of thermodynamics, and the quantity that measures the disorder is called entropy. Entropy increases in the direction we call the future, and it decreases in the direction we call the past. This statistical asymmetry, rather than any feature of the geometry, is what gives time its apparent arrow. To see how this works, consider a glass of water with an ice cube floating in it. The ice cube is highly ordered. Its molecules are arranged in a regular crystalline lattice. The water around it is less ordered. Its molecules are moving around freely, colliding with one another, exchanging energy. Over time, energy flows from the warmer water to the cooler ice. The ice melts, and the contents of the glass become uniformly water at a single temperature. The final state is more disordered than the initial state, in the precise sense that there are vastly more ways to arrange the molecules of liquid water at a given temperature than there are to arrange some of them in a crystalline lattice and the rest in a slightly warmer liquid. The increase in disorder is what entropy measures, and the reason the process goes in this direction, rather than the reverse, is simply that the disordered states are far more numerous than the ordered ones. If you start with the ordered state and let the system evolve randomly, it will almost certainly end up in a disordered state, because there are so many more disordered states to end up in. The reverse process, water spontaneously separating into ice and warmer water, is not forbidden by the equations of physics. It is just spectacularly unlikely, so unlikely that in the entire history of the observable universe, it would not be expected to happen even once for any glass of water you might prepare. This statistical argument, due originally to Ludwig Boltzmann in the late 19th century, gives us a powerful explanation for why time appears to have a direction. But it raises an immediate question. If the equations are time-symmetric, and if entropy increases in one direction simply because disordered states are more numerous, then why is entropy lower in the past than in the future? Why did the universe ever exist in a low entropy state in the first place? The statistical argument tells us that entropy will increase from any given state. It does not tell us why the starting state was so low in entropy that the increase has been going on for billions of years and shows no signs of stopping. The answer to this question, as far as physics has been able to provide one, points to the very beginning of the universe. The early universe, in the conditions that prevailed just after what we call the Big Bang, was in a state of remarkably low entropy compared to what it could have been. The reasons for this are not fully understood, and they touch on some of the deepest unresolved problems in cosmology. But the empirical fact is clear. The universe began in a low entropy state, and it has been moving toward higher entropy ever since. This evolution is what gives time its arrow. It is not that time itself points from past to future. It is that the contents of the universe are arranged in such a way that one direction along the time dimension looks like the past, the direction of low entropy, and the other looks like the future, the direction of high entropy. In the eternalist picture, this thermodynamic asymmetry is a feature of the four-dimensional structure itself, not a feature of any flow within the structure. The block universe contains a region of very low entropy at one end, the cosmological beginning, and regions of progressively higher entropy as you move toward the other end. The world lines that thread through the block, including the world lines of conscious observers, pass through these regions in a particular sequence. They begin in lower entropy environments and proceed to higher entropy ones. This is why memory works the way it does. Memory is a physical process that requires entropy to increase in order to record information reliably. The very act of forming a memory involves an increase in entropy somewhere in the system that is doing the remembering. Memories of the past are possible because the past has lower entropy. Memories of the future are impossible because the future has higher entropy. And the asymmetry of entropy is what makes one direction available to memory and the other direction inaccessible. This is a remarkable conclusion. It says that the felt directionality of time, the sense that we are moving from a past we remember toward a future we do not, is not a feature of time itself, but a feature of the thermodynamic gradient in which we happen to find ourselves. If we were somehow located in a region of the universe where entropy was decreasing rather than increasing, we would experience time as running in the opposite direction. We would remember what we now call the future, and we would anticipate what we now call the past. The geometry of spacetime would be unchanged, the contents would be arranged differently, and our experience would follow the gradient, whichever way it happened to point. There is something almost vertiginous about this idea, and it has been the subject of considerable speculation. Some physicists have wondered whether there might be regions of the universe, perhaps very far away, where the thermodynamic gradient runs in the opposite direction from ours. If such regions exist, they would contain observers for whom time runs backward, in the sense that their memories accumulate in the direction we call the past. These observers would not perceive themselves as living backward. They would perceive themselves as living forward, because forward, for them, would mean toward higher entropy, which would be in the direction we call earlier. The two civilizations could, in principle, look at each other and see each other living in reverse. The question of which direction is the real forward would have no objective answer. It would depend on the local thermodynamic gradient and nothing more. This kind of speculation is not idle. It bears on serious questions about the nature of the universe at very large scales. The observable universe appears to have a single thermodynamic gradient, with entropy increasing in a single direction throughout. But the observable universe is only a small portion of what may exist. The full universe, if it is much larger or even infinite, might contain regions with different gradients. The arrow of time, in this view, would be a local phenomenon, not a universal one. Different parts of the block universe would have different arrows, depending on the arrangement of matter and energy in those parts. The block as a whole would not have a preferred direction, only its inhabitants would, and only locally. There is a deeper puzzle here, which has been called the past hypothesis. The puzzle is this. We can explain why entropy increases by appealing to statistical arguments. We can show that disordered states are more numerous than ordered ones. But we cannot, from within physics, explain why the universe started in such an extraordinarily ordered state to begin with. The initial conditions of the universe were so finely tuned in terms of entropy that the probability of them occurring by chance is effectively zero. This is sometimes called the problem of the low entropy past, and it has generated considerable debate. Some physicists argue that the low entropy initial state is simply a boundary condition that has to be accepted as given, like the speed of light or the mass of the electron. Others argue that there must be some deeper reason for it, perhaps involving the structure of the universe at very early times, or perhaps involving a multiverse in which our universe happens to be one of the rare ones with a low entropy past. Whatever the explanation, the existence of the low entropy past is what gives time its apparent direction. And in the eternalist picture, this is not a fact about time, but a fact about the four-dimensional structure of the universe. The structure has a particular shape. One end of it is highly ordered, the other end is increasingly disordered. World lines that thread through it experience the gradient as the flow of time. The flow is not in the geometry, it is in the contents. This raises a subtle point about the relationship between the geometric picture and the experiential picture. The geometric picture says that all moments exist together, that the block is complete, that nothing is being added or subtracted. The experiential picture says that time flows, that the present is special, that the future is becoming the past. The two pictures are not in contradiction if we accept the eternalist response. The experiential picture describes what it is like to be a world line traversing the block. The geometric picture describes the block itself. The flow that is experienced is the experience of traversing a gradient. The block, viewed from outside, has no flow, but there is no view from outside available to anyone inside the block. We are all inside, all moving along our world lines, all experiencing the gradient. The flow is real for us, even if it is not real for the block. This is one of the most important conceptual points in the eternalist picture, and it is also one of the most easily misunderstood. Eternalism does not deny that time appears to flow. It does not deny that the present feels special. It does not deny any of the data of conscious experience. What it denies is that these features of experience correspond to features of the underlying reality. They are features of how the underlying reality looks from the inside, from the perspective of a world line embedded in the block. The block itself does not flow. The block contains the flow. The thermodynamic arrow, then, is the bridge between the two pictures. It explains why time appears to have a direction even if the underlying geometry does not. It explains why the past is fixed and the future is not, in the sense that memories of the past are possible and memories of the future are not. And it explains why the present feels special, because the present is the moment along the world line at which the next memory is being formed, the next experience is being registered, the next increase in entropy is being inscribed into the structure of the brain. The present is special in this sense, not because the universe singles it out, but because each observer's world line is anchored at a particular point along the gradient, and that point is where the observer's active engagement with the world is taking place. This is enough to account for the experience of time flowing, even in a static block. But it does not exhaust the strangeness of the eternalist picture. There are further consequences having to do with the possibility of revisiting earlier moments, of revisiting earlier coordinates in the block that the geometry itself appears to allow. The equations of general relativity, under certain conditions, permit world lines that close back on themselves, returning to events they have already passed through. What such returns would mean, and whether they could ever actually occur, is one of the strangest implications of the geometry we have been describing. The standard image of a world line is a curve that proceeds steadily through the block, moving from earlier coordinates to later ones, never doubling back. This is the world line of an ordinary object: a particle, a planet, a person. Each of these traces a path through space-time that advances along the time dimension in a single direction. The path may curve as the object moves through space, may accelerate or decelerate, may interact with other world lines through forces and collisions, but it does not turn around and revisit earlier events. The thermodynamic arrow, the local gradient of entropy, ensures that every ordinary object experiences time as flowing forward, and the geometry of space-time, under normal conditions, does not provide any pathway by which a world line could return to an event it has already passed through. But the equations of general relativity, examined carefully, do not absolutely forbid such pathways. They permit, under certain conditions, the existence of world lines that close back on themselves, that return to their own past, that form loops in the four-dimensional structure. These are called closed timelike curves, and they have been the subject of intense theoretical investigation ever since they were first identified. The first explicit example was found by Kurt Gödel, the same logician who had proven the famous incompleteness theorems in 1949. Gödel was a friend of Einstein at the Institute for Advanced Study in Princeton, and he discovered that the equations of general relativity admit solutions in which the entire universe is rotating, and in such a rotating universe, paths exist along which an observer could travel into their own past. Gödel presented this solution to Einstein as a kind of birthday gift, and Einstein responded with characteristic seriousness. He acknowledged that the solution was mathematically valid, and he expressed concern about what it meant for the consistency of physics. He hoped, but could not prove, that physical reasons might rule out such solutions even though the equations did not. The Gödel universe is not our universe. Our universe is not rotating in the way his solution requires. But the discovery established a precedent. The equations themselves, the equations that describe the gravitational behavior of matter and energy in four-dimensional spacetime, do not exclude the possibility of closed time-like curves. They merely require certain configurations of matter and energy to produce them. Subsequent investigations have identified other configurations that would allow them. Wormholes, hypothetical tunnels connecting distant regions of spacetime, are one example. If a wormhole could be constructed and stabilized, it could in principle be manipulated to create closed time-like curves between its two mouths. Cosmic strings, hypothetical one-dimensional defects in spacetime that might have formed in the early universe, are another example. Pairs of cosmic strings moving past each other under certain conditions could also produce closed time-like curves. None of these configurations have been observed in nature, and none of them have been produced in any laboratory. But the equations permit them. The geometry does not in itself rule them out. What would it mean for the eternalist picture if closed time-like curves actually existed? The implications are subtle and somewhat counterintuitive. The block universe is a structure in which all moments coexist. If a world line forms a closed loop, it does not violate the existence of the block. The loop is just a particular shape that the world line traces within the four-dimensional structure. From the perspective of the block, the loop is complete. It has no beginning and no end. It is simply a closed curve, like a circle drawn on a piece of paper. The world line visits the same coordinates more than once, but this does not require those coordinates to be visited in any particular sequence. The visits are part of the structure. They are there because the geometry permits them and because the world line happens to follow a path that includes them. This way of describing closed time-like curves dissolves some of the paradoxes that have plagued discussions of time travel. The classic paradox is the grandfather paradox. If you could travel into your own past, the argument goes, you could prevent your grandfather from meeting your grandmother, which would prevent your own birth, which would prevent you from ever traveling into the past in the first place. The contradiction seems irreparable. But in the eternalist picture, the paradox does not arise in this form. The world line that includes the time traveler and the events they participate in is a complete structure within the block. If the structure includes a journey to the past, it also includes the consequences of that journey, and those consequences must be consistent with the structure itself. The grandfather either was prevented from meeting the grandmother, in which case the time traveler never existed, in which case the journey never happened, in which case the prevention never occurred, or the grandfather was not prevented, in which case the time traveler did exist, in which case the journey did happen, but its outcome was something other than preventing the meeting. The block contains only consistent histories. Inconsistent histories simply do not appear in it. This is sometimes called the principle of self-consistency, and it has been formalized by physicists working on the implications of closed timelike curves. The principle states that, in the presence of such curves, the only events that can occur are those that form globally consistent histories. Any inconsistent history is simply impossible, not because something prevents it from happening, but because the geometry of the block does not contain it. A time traveler who attempted to do something inconsistent would find, in ways that might seem improbable but would always work out, that their attempt failed or was redirected. The gun would jam. The bullet would miss. The grandfather would already have left the building. The mechanisms by which consistency is maintained could be subtle, and they might involve a great deal of apparent coincidence, but the consistency itself would be inevitable. There is something deeply strange about this picture, and there is also something that fits comfortably with the eternalist framework. The strangeness lies in the implication that the block universe, if it contains closed time-like curves, is a structure in which the very notion of free action is constrained in a peculiar way. You cannot, in such a structure, do anything that is inconsistent with what you have already done, even if what you have already done lies in your future according to your local thermodynamic gradient. The constraints are not imposed by any external force. They are imposed by the geometry itself. The block is what it is. The world lines within it are what they are. If they include closed loops, then the loops are consistent. If they do not include closed loops, then they extend in one direction along the time dimension without returning. The fit with the eternalist framework lies in the fact that this is not actually different in kind from the situation we have already been describing. In the standard block universe without closed time-like curves, the world lines are also fixed structures. Your world line includes every event you have experienced and every event you will experience, all laid out in the block. You cannot, in any meaningful sense, change your world line, because your world line is the structure that contains your experiences. If you make a different choice tomorrow than you would have otherwise made, the different choice is part of your world line, and the choice you would have otherwise made is not. There is no parallel version of your world line with the other choice. There is just the one world line you actually have, with the choices it actually contains. Closed time-like curves do not introduce a new kind of constraint. They introduce a more elaborate version of the same constraint. The block contains all and only the events that occur. Inconsistent events do not occur, whether they involve traveling to the past or not. It is worth noting that most physicists are skeptical that closed time-like curves actually exist in the real universe, even though the equations of general relativity permit them. There are several reasons for this skepticism. The configurations of matter and energy required to produce them are extreme, often involving exotic forms of matter with properties that have never been observed. The known forms of matter do not appear to be capable of producing such configurations under any natural circumstances. There are also theoretical arguments due to Stephen Hawking and others, suggesting that quantum effects might prevent closed time-like curves from ever forming, even if the classical equations would otherwise permit them. Hawking proposed what he called the chronology protection conjecture, which states that the laws of physics conspire to prevent the formation of closed time-like curves on macroscopic scales. The conjecture has not been proven, but there is suggestive evidence for it in various calculations. If the chronology protection conjecture is correct, then the block universe in which we live does not contain any closed loops. Every world line extends in one direction along the time dimension, from its beginning to its end, without returning to its own past. The block is a structure with a definite arrow, in the sense that the world lines all proceed in the same general direction along the time dimension. This direction is set by the thermodynamic gradient, and it is the same direction everywhere within the observable universe. The block is, in a sense, well behaved. It allows for the eternalist picture without introducing the strange complications of self-consistent loops. If the chronology protection conjecture is wrong, then the block universe could contain closed loops, and the picture becomes more elaborate but not fundamentally different. The block still exists as a complete structure. The world lines within it are still fixed. The events that occur are still all and only the events that the structure contains. The principle of self-consistency ensures that everything fits together. The strangeness of being able to revisit earlier coordinates is real, but it does not introduce any logical contradictions. The block can accommodate it. The question of whether closed timelike curves exist in our universe is, at present, unresolved. There are no observations that confirm them, and there are no observations that definitively rule them out. The theoretical situation is similar. The equations permit them under certain conditions. Other considerations may rule them out, but the rulings are not yet definitive. What we can say is that the eternalist picture is consistent with their existence, and it is also consistent with their non-existence. The picture does not depend on the answer. The block universe is the block universe, whether or not it contains loops. There is one more aspect of this discussion that deserves attention. The geometry of general relativity is classical. It describes spacetime as a smooth manifold with definite properties at every point, evolving according to deterministic equations. But the universe is not, at the fundamental level, classical. It is quantum mechanical. And the introduction of quantum mechanics into the eternalist picture creates complications that the classical geometry does not anticipate. The block universe of general relativity is, in some sense, an approximation. The full picture, if we could obtain it, would have to incorporate the strange features of quantum theory, the probabilities, the superpositions, the measurements, the apparent role of observation in determining what is real. How these features fit into the four-dimensional structure is a question that has occupied some of the most ambitious physicists of the past century. The answers, such as they are not yet complete, but they point in directions that are even stranger than the classical block, and they raise questions about whether the block, as classical relativity describes it, is the right picture at all. Quantum mechanics is the most successfully tested theory in the history of physics. Its predictions have been confirmed to extraordinary precision in every experiment that has been performed to test them. The behavior of atoms, molecules, electrons, photons, and the countless interactions among them follow the rules of quantum theory with a fidelity that has never been violated. And yet, despite this empirical success, the interpretation of quantum mechanics remains contested. Physicists agree on how to calculate the predictions. They disagree, sometimes vehemently, on what those predictions mean about the nature of reality. The disagreements touch directly on the questions we have been examining, because quantum mechanics introduces features that do not fit easily into the classical block universe of relativity. The central peculiarity of quantum mechanics is that it does not describe definite states, it describes probabilities. A particle, in the quantum formalism, does not have a definite position and a definite velocity at every moment. It has a wave function, a mathematical object that encodes the probabilities of finding the particle in various locations or with various velocities when a measurement is performed. Before a measurement, the particle is in what is called a superposition, a kind of weighted combination of all the possible states it could be in. When a measurement occurs, the superposition collapses, and the particle is found to be in one specific state. The probability of being found in any particular state is determined by the wave function. The outcome of any individual measurement is not determined by the wave function, it is only the probabilities that are determined. The actual outcome appears to be, in some deep sense, random. This randomness is not the randomness of incomplete information. In classical physics, when we say something is random, we usually mean that we do not know all the details that would determine its behavior. A roll of a die appears random because we cannot track all the forces and torques acting on the die. But if we could in principle predict the outcome. In quantum mechanics, the randomness is different. It does not appear to be the result of missing information. It appears to be fundamental, built into the structure of the theory. No matter how much information you have about a quantum system, you cannot predict the outcome of an individual measurement with certainty. You can only predict the probabilities. This is one of the most strenuously tested features of quantum mechanics, and it has survived every attempt to find hidden variables that would restore determinism. The randomness, as far as we can tell, is real. This feature creates an immediate tension with the block universe picture. The block universe of classical relativity is deterministic in a strong sense. The entire four-dimensional structure is laid out, with every event at its coordinates, complete and unchanging. The future, in this picture, is as definite as the past. It is already there, waiting to be reached by world lines that have not yet arrived. But quantum mechanics suggests that the future is not so definite. The outcomes of quantum measurements are not determined in advance. They are determined at the moment of measurement, and the determination is probabilistic rather than necessary. This appears to conflict with the eternalist picture in a fundamental way. There are several responses to this tension, and they correspond to different interpretations of quantum mechanics. Each interpretation has its defenders and its critics, and none of them is universally accepted. They all make the same predictions for experimental outcomes, which is why they are interpretations rather than competing theories. But they paint very different pictures of what is actually happening in the world. The first response, often called the Copenhagen interpretation, holds that the wave function is not a description of physical reality, but a description of our knowledge about physical reality. The collapse of the wave function during a measurement is not a physical process, but an update of our information. In this view, the questions about what quantum systems are doing between measurements are not meaningful questions. The theory only tells us what we will find when we measure. It does not tell us what is happening when we are not measuring. This view fits awkwardly with the block universe, because it seems to deny that there is a definite reality independent of observation. But it has the advantage of being agnostic about the metaphysics. It treats quantum mechanics as a tool for predicting measurement outcomes, and it does not commit to any deeper picture. The second response, often called the many worlds interpretation, takes the wave function entirely seriously as a description of physical reality. In this view, the wave function never collapses. The superposition continues to evolve, even through measurement. What appears to be collapse is actually the splitting of the universe into multiple branches, one for each possible outcome of the measurement. In each branch, a version of the observer sees a different outcome, and each version believes their outcome is the only one that happened. The branches do not interact with one another, so each version of the observer is unaware of the others. The total wave function of the universe, in this view, is a vast superposition of all possible histories, all of which are equally real. The randomness of quantum measurements becomes an illusion. All outcomes occur. The observer simply finds themselves in one branch rather than another, and the apparent randomness is just the question of which branch they happen to be in. The many worlds interpretation has a certain compatibility with the eternalist picture, but it transforms it. Instead of a single four-dimensional block containing one definite history, the universe becomes a vast structure containing all possible histories, branching at every quantum event. The block is no longer a singular object. It is a branching tree, or perhaps more accurately, a kind of high-dimensional manifold in which every possible sequence of events is realized somewhere. The future, in this view, is not undetermined. It is overdetermined. Every possible future occurs. The question is not what will happen, but which branch the observer ends up in. And even that question may not have a fully meaningful answer, because in the many worlds picture, every version of the observer follows their own branch and is unaware of the others. The third response, sometimes called the relational interpretation, holds that the properties of quantum systems are not absolute, but relative to the systems with which they interact. A particle does not have a definite position. It has a position relative to a particular observer or measuring device. Different observers can have different relationships with the same system, and there is no observer-independent fact about what the system is doing. This view has some affinities with relativity, where simultaneity is also observer-dependent. It treats the apparent definiteness of measurement outcomes as a feature of the relationship between the observer and the observed, not as a feature of the observed alone. How this fits into the eternalist picture is not entirely clear, but it suggests a block universe in which the contents are not absolute, but depend on the network of relationships that constitute them. The fourth response, often called the de Broglie-Bohm interpretation or pilot wave theory, restores determinism by introducing hidden variables that supplement the wave function. In this view, particles do have definite positions at all times, but their motions are guided by the wave function in a way that produces the observed quantum probabilities when measurements are performed. The theory is deterministic in the sense that the initial conditions plus the wave function determine all future positions. The apparent randomness of measurements is the result of our ignorance of the precise initial conditions. This view is the most compatible with the classical block universe because it preserves determinism. But it has features that are awkward for relativity, including a kind of non-locality that some physicists find unappealing. Each of these interpretations has its strengths and weaknesses. None of them is fully satisfactory, and the debate among them continues. What they all share is the recognition that quantum mechanics complicates the eternalist picture in significant ways. The classical block universe of relativity, with its definite four-dimensional structure and its complete laying out of all events, has to be modified to accommodate quantum theory. The modifications are different in different interpretations, but they all suggest that the simple picture we have been describing is, at best, an approximation. There is a deeper question lurking here, which has to do with the relationship between quantum mechanics and general relativity. The two theories are the great pillars of modern physics. Quantum mechanics governs the behavior of matter at small scales. General relativity governs the behavior of spacetime at large scales. In most circumstances, the two theories operate in different regimes and do not interfere with each other. But there are situations in which they should both apply, and in those situations, they do not fit together. The interior of a black hole, the very early universe, the smallest scales of spacetime itself, all require a theory that combines quantum mechanics and gravity. Such a theory has not yet been developed. Various candidates exist, including string theory and loop quantum gravity, but none of them has been confirmed by experiment. The unification of quantum mechanics and general relativity is one of the great unsolved problems of physics, and its solution would likely transform our understanding of time itself. One of the most striking features of attempts to combine quantum mechanics and gravity is that in many of these attempts, time disappears as a fundamental variable. The equations that emerge do not have a time coordinate in the usual sense. They describe relationships among the various features of the universe, but they do not describe how those features evolve in time. Time, in these theories, is not a parameter that runs alongside the rest of physics. It is an emergent feature, something that arises from the underlying structure, but is not itself part of that structure. This is a remarkable possibility, and it has been called the problem of time in quantum gravity. If the fundamental equations do not have time in them, then where does time come from? How does our experience of time emerge from a structure that does not contain it? The most famous expression of this problem is found in an equation called the Wheeler-DeWitt equation, named after John Wheeler and Bryce DeWitt, who derived it in the 1960s as an attempt to formulate quantum mechanics for the entire universe. The equation describes the wave function of the universe, and it has the peculiar feature that it does not include any time dependence. The wave function in this equation does not evolve, it just is. The universe, as described by the Wheeler-DeWitt equation, is in some sense timeless. It is a fixed state, not a process. This is of course similar to the eternalist picture of the block universe, but it is more extreme. The block universe has time as a dimension, even if not as a flow. The Wheeler-DeWitt universe does not even have time as a dimension. It is something else, something that may give rise to the appearance of time, but does not contain time itself. How can we understand a universe in which time is not a fundamental feature, but an emergent one? The question is at the frontier of theoretical physics, and the answers are speculative. One approach is to suggest that time emerges from the entanglement among the parts of the universe. When two subsystems become entangled, correlations develop between them, and from the perspective of one subsystem, the other appears to be evolving in time. Time, in this view, is what entanglement looks like from the inside. Another approach is to suggest that time is a thermodynamic phenomenon, emerging from the statistical behavior of the underlying degrees of freedom, much as temperature emerges from the kinetic energy of molecules. Time, in this view, is not a feature of the fundamental theory, but a feature of the macroscopic limit. A third approach, related but distinct, is to suggest that time is an aspect of the geometry of the universe itself, emerging from the way the various pieces of spacetime fit together at the smallest scales. These approaches are not yet settled science. They are research programs, areas of active investigation, with strong proponents and serious critics. But they all share a common implication. Time at the fundamental level may not exist. The universe may be, at its deepest level, something timeless, and the time we experience may be a property of how we, as observers within the structure, perceive what is around us. The eternalist picture, in this light, is not just a claim about relativity. It is a claim that connects to some of the deepest speculations in modern physics. The block universe may be more than a block. It may be a structure in which time is not even a coordinate, but an emergent feature arising from something more fundamental that we are only beginning to glimpse. The Wheeler-DeWitt equation deserves a closer examination because it represents one of the most direct confrontations between modern physics and the question of whether time is fundamental. The equation was derived in the late 1960s as part of an effort to combine quantum mechanics with general relativity. John Wheeler, an American physicist of remarkable imagination, had been pondering how to apply the rules of quantum theory to the universe as a whole, treating spacetime itself as a quantum object. DeWitt, working independently and then in collaboration with Wheeler, developed the mathematical formulation. The result was an equation that purported to describe the wave function of the entire universe, the quantum state of all of spacetime and all of its contents, treated as a single object subject to quantum rules. When the equation was written down, something unexpected emerged. The equation had a structure familiar from quantum mechanics, but it lacked a feature that every other quantum equation possessed. It had no time dependence. In ordinary quantum mechanics, the wave function of a system evolves over time according to the Schrödinger equation, which explicitly contains a time derivative. The wave function changes as time advances. Probabilities shift, states develop. The equation describes a process, but the Wheeler-DeWitt equation contains no such time derivative. The wave function of the universe in this formulation does not change. It does not evolve. It simply satisfies an equation that holds at every point in some abstract configuration space, with no notion of one configuration being earlier or later than another. The equation is, in a precise mathematical sense, timeless. This result was, and remains, deeply puzzling. If the fundamental equation governing the quantum state of the universe contains no time, then in what sense does time exist at all? How does the appearance of temporal evolution emerge from a structure that, at its most basic level, does not evolve? The puzzle is not a minor technicality. It is a serious challenge to the way we think about physics. Every other equation in physics is an equation about how things change. Newton's laws describe how positions and velocities change in time. Maxwell's equations describe how electric and magnetic fields change in time. The Schrödinger equation describes how quantum wave functions change in time. The equations of general relativity describe how the geometry of spacetime changes in response to its contents, though the time variable is more subtle in this case. But the Wheeler-DeWitt equation does not describe change. It describes a static condition that the wave function of the universe must satisfy. There are several ways physicists have tried to make sense of this. One approach is to argue that time is, in fact, not fundamental, and that the timelessness of the Wheeler-DeWitt equation is a feature rather than a bug. In this view, the equation reveals something deep about reality. The universe, at the most fundamental level, is not a process unfolding in time. It is a static structure, a kind of frozen configuration that contains all the information necessary to describe everything that exists. Time emerges from this structure as a way of describing relationships among different parts of the configuration. The appearance of temporal evolution is not an illusion exactly, but it is not a fundamental feature of reality either. It is a feature of how we, as observers embedded within the configuration, perceive the relationships among its parts. This is a radical claim, and it goes beyond even the standard block universe of classical relativity. The classical block universe still has time as one of its dimensions. Time is not a flow, but it is a coordinate, a way of organizing the four-dimensional structure. The Wheeler-DeWitt picture suggests something more extreme. Time is not even a coordinate at the fundamental level. It is something that emerges from a structure that does not in itself contain it. The structure is configurational rather than temporal. It describes possible arrangements of matter and energy and geometry, but it does not order those arrangements into a sequence. The sequencing happens at a higher level in the relationships among the arrangements, in the way that observers within the structure perceive correlations between different parts. A second approach is to argue that time is hidden in the Wheeler-DeWitt equation in a way that is not immediately obvious. The equation may not have an explicit time variable, but it may have implicit time variables, quantities that play the role of time without being labeled as such. The geometry of the universe, for example, changes from configuration to configuration in the wave function, and these changes can be used to define a kind of clock. The expansion of the universe provides one such clock. The growth of structure within the universe provides another. The accumulation of entropy provides a third. Each of these quantities increases monotonically in the direction we call the future, and any of them could serve as a stand-in for the time variable that is missing from the explicit formulation. Time, in this view, is not absent from the equation. It is just not written in the form we expected. A third approach is to argue that the Wheeler-DeWitt equation is incomplete. It may capture some features of quantum gravity, but miss others. A more complete theory might restore time to its usual role as an explicit variable. This view tends to be held by physicists who are skeptical of the timeless picture and who suspect that the absence of time in the Wheeler-DeWitt equation is a sign that something is missing. The development of more complete theories of quantum gravity, including string theory and loop quantum gravity, has not yet resolved this question. Both theories grapple with the issue of time, and both have suggestions for how time might emerge from a more fundamental structure, but neither has produced a definitive answer. The implications of a fundamentally timeless universe are profound. If time is not fundamental, then the eternalist picture takes on an even stronger character. The block universe is not merely a four-dimensional structure in which all moments coexist. It is a structure in which the very notion of moment is derivative, emerging from relationships within a more basic configuration. The moments we experience as separate, the past, present, and future that we organize our lives around, may be features of how the universe looks from the inside rather than features of the universe itself. They may be aspects of how a particular observer carves up a structure that is, in itself, undifferentiated along anything we would recognize as a time axis. This is, of course, very difficult to picture. Human beings have no native way to imagine a structure that is not arranged in time. Our language is saturated with temporal terms. Our thinking is temporal. Our experience is temporal. Even when we try to describe a timeless structure, we end up using temporal language, talking about what the structure contains or what it includes, as if these were events occurring within time. The language betrays the underlying assumption that time is the medium of existence. To genuinely think outside of this assumption is a kind of conceptual achievement that few people have attempted, and even fewer have succeeded at. One physicist who has attempted it is Julian Barbour, a British researcher who has spent decades developing a theory in which time is entirely absent. In Barbour's view, the universe is a vast collection of configurations, each of which is a possible arrangement of all the matter and energy in existence. These configurations form a high-dimensional space, which Barbour calls Platonia, after the philosopher Plato, who held that abstract forms had a kind of timeless existence. Each point in Platonia is a complete description of a possible universe at what we would call an instant, though Barbour insists that the word instant is misleading because there is no time in which the configurations occur. The configurations simply exist, all of them, as elements of a timeless space. The appearance of temporal evolution arises from the way the configurations are related to one another. Some configurations contain records that point to other configurations, in the sense that the second configuration could plausibly have arisen from the first by the kinds of processes we observe. These records create the illusion of history. They make it seem, from within a given configuration, as if there were a sequence of events leading up to it. But there is no actual sequence. There are only configurations and the records they contain. Barbour's view is one extreme version of the timeless picture, and it is not universally accepted. But it illustrates how seriously some physicists take the possibility that time is not fundamental. The Wheeler-DeWitt equation is the technical anchor for views of this kind. It provides a mathematical formulation in which the absence of time can be examined precisely. Whether Barbour's interpretation is correct or whether some other interpretation will prove more accurate, the equation itself stands as a remarkable fact about modern physics. It is the equation that, when applied to the universe as a whole, does not describe a process, it describes a state. The relationship between the Wheeler-DeWitt equation and the eternalist picture is worth examining carefully. The classical block universe of relativity is consistent with the equation, but it is also more than the equation requires. The block universe has time as a dimension. The Wheeler-DeWitt picture does not require time even as a dimension. The block universe organizes events into world lines that have a definite ordering along the time axis. The Wheeler-DeWitt picture treats configurations as elements of an abstract space without any inherent ordering. The block universe still talks about events. The Wheeler-DeWitt picture may not even have events in the usual sense. It has configurations, and the configurations are related to one another by the structure of the wave function, but the relations are not necessarily temporal. This raises a question that the simpler eternalist picture does not have to address. If time is not fundamental, then what does it mean to say that all moments exist simultaneously? The very phrase contains a temporal term. Simultaneously means at the same time. If there is no time at the fundamental level, then there is no simultaneity in the ordinary sense. The moments do not coexist in time. They simply coexist as elements of a structure that is itself outside of time. The eternalist claim, in this fully timeless picture, becomes something stronger and stranger. It is not that all moments are equally real. It is that the notion of moment, of a slice of reality at a particular time, is itself a feature of how the structure looks from the inside, not a feature of the structure itself. This is enough to make one's head spin, and it is meant to. The conceptual demands of the timeless picture exceed the demands of the classical block universe, which already exceed the demands of ordinary temporal thinking. We are asked to imagine, or at least to acknowledge the possibility, that the most fundamental features of our experience, the flow of time, the distinction between past and future, the very notion of moments, may not correspond to anything in the underlying reality. They may be artifacts of our position within a structure that does not have these features. The structure has whatever it has. We carve it up into temporal slices because we are the kind of beings for whom temporal slicing is the natural mode of perception. But the slicing is ours, not the structure's. There is one more aspect of this that deserves mention. If the universe is fundamentally timeless, then the question of what consciousness is and how it relates to the structure becomes especially pressing. Consciousness, as we experience it, is temporal. It is a flow of awareness, a sequence of perceptions and thoughts, a feeling of being engaged with the present moment. If the underlying reality has no time, then consciousness must be something that imposes time on the structure or something that is itself an emergent feature of the structure. How a timeless structure could give rise to temporal experience is one of the deepest questions raised by the eternalist picture, and it is a question to which we must now turn. Consciousness in the eternalist picture occupies a peculiar position. On one hand, it is the source of all our concern about time. We notice the flow of time, we experience the present as special, we remember the past and anticipate the future, all through the operations of consciousness. Without conscious experience, the question of whether time flows would not even arise. The universe would just be whatever it is, without anyone to wonder about it. On the other hand, consciousness itself is something that occurs within the universe, something that arises from the physical processes of brains, and therefore something that must, presumably, be describable in terms of the same four-dimensional structure that contains everything else. If the structure is static, then conscious experience must somehow emerge from a static structure. If the structure has no fundamental time, then the temporal character of consciousness must be derived from something non-temporal. These are challenging propositions, and they raise questions that philosophy and physics together have not yet resolved. Consider what consciousness looks like when described in physical terms. The brain is a vast network of neurons, each of which interacts with thousands of others through electrochemical signals. The pattern of neural activity at any given moment is correlated with the contents of conscious experience. When you see a red apple, certain neurons fire in patterns associated with the perception of red and the recognition of apples. When you feel sad, other patterns of neural activity occur. The correlation between neural patterns and conscious experience is one of the most studied phenomena in neuroscience, and while many details remain unclear, the general principle is well established. Consciousness, whatever it ultimately is closely tied to the physical activity of brains. In the eternalist picture, this physical activity is part of the four-dimensional structure of the universe. The brain has a world line. Actually, the brain has many world lines, one for each of its constituent particles, all woven together into the more complex world line of the brain as a whole. The neural firings, the chemical reactions, the synaptic transmissions, all of these are events at definite coordinates in the block. They are arranged in a particular sequence along the time dimension, with earlier firings preceding later ones, and the entire history of the brain is laid out as a four-dimensional pattern. Consciousness, on this view, is whatever it is that this pattern gives rise to, when the pattern has the right kind of complexity and organization. If the block universe is static, then the entire history of a conscious being is already present in the structure. Your birth, your first memory, your first heartbreak, your last breath, all of them are at their coordinates, complete and unchanging. The young version of you, the middle-aged version of you, the old version of you, all exist within the structure. They are not stages that you have passed through and left behind. They are different segments of your world line, each as real as the others. The you of yesterday is just as much you as the you of today, in the sense that both are part of the same continuous world line winding through the block. The fact that you, today, can only access the memories that are stored in your present brain state does not mean that your past self has ceased to exist. It means that the past self is at coordinates you cannot revisit, but those coordinates are still occupied. This raises an immediate question. If all the versions of you exist simultaneously, what is the relationship among them? Are they separate beings or are they parts of a single being? The eternalist answer is that they are parts of a single world line, and that the world line is what constitutes the person. The person is not a momentary slice of awareness. The person is the entire four-dimensional extent of their existence, from beginning to end. The momentary slice that you call yourself right now is just one cross-section of a longer object. You are, in a sense, larger than you usually think. You extend not just in space, occupying the volume of your body, but in time, occupying the duration of your life. The you of this moment is only a small part of the full extent of who you are. This way of thinking about personal identity has some odd consequences. It suggests that the relationship between you now and you yesterday is not the relationship between a present being and a past being. It is the relationship between two parts of the same being, two segments of the same world line. The you of yesterday is no more gone than your left foot is gone when you focus on your right hand. Both are still there, parts of the larger structure that is you. The difference is that the you of yesterday is at a different time coordinate, while your left foot is at a different space coordinate. The dimensions are different, but the principle is the same. You are extended across all of them. The same logic applies to people who have died. In the eternalist picture, the dead are not gone in the sense of having been erased. Their world lines are still part of the block, occupying their assigned coordinates. The grandmother who passed away years ago is still there, in the structure, at the coordinates where her world line existed. You cannot reach her. You cannot communicate with her. But she is not, in this picture, a thing that no longer exists. She's a thing that exists at coordinates you cannot access. The difference between these two formulations may seem subtle, but it is significant. Erasure implies absence. Inaccessibility implies presence elsewhere. The eternalist picture replaces the first with the second. This has been a source of strange comfort for some people who have encountered the eternalist picture. The idea that the moments of one's life, including the moments of one's loved ones, are permanent features of reality, that they have not been wiped away but only moved to a different region of the structure, can feel like a form of solace in the face of loss. It does not bring back the dead in any practical sense. It does not restore relationships that have ended, but it suggests that the relationships, while they existed, will always have existed, in a way that the presentist picture cannot quite capture. In presentism, what is past is gone, and what is gone is no longer anywhere. In eternalism, what is past is elsewhere, still occupying its place in the four-dimensional structure. But the picture also has uncomfortable implications, and these deserve equal attention. If the entire history of a person is fixed in the block, then so is the entire future. The version of you that will exist next year is already there. The version of you that will exist on your deathbed is already there. The exact circumstances of your last moments, whatever they are already part of the structure. You will reach them in due course, but they are not waiting to be created. They are waiting to be inhabited. This can be troubling. It suggests that there is something inevitable about everything that will happen to you. Your future joys are inevitable. So are your future losses. The decisions you will make, the people you will meet, the misfortunes that will befall you, all of them are fixed features of the structure, complete and unchanging. How should one feel about this? Different temperaments respond differently. Some people find it liberating in the sense that it removes the burden of trying to control what cannot be controlled. If the future is already there, then anxiety about shaping it becomes pointless. You will reach what you reach. The structure is what it is. You can act, you can strive, you can plan, but the outcomes are already part of the block. The role of effort and choice in the eternalist picture is a subtle one, which we will consider more carefully in a moment. But for now, the point is that the fixity of the future need not be experienced as oppressive. It can be experienced as the way things simply are, neither good nor bad in itself. Other people find it disturbing in the sense that it seems to deny the openness of the future that they value. If everything is fixed, then there is no genuine possibility, no real alternative, no actual choice. What looks like deliberation is just the unfolding of a predetermined sequence. What feels like decision is just the experience of being a world line that passes through a particular pattern of events. This way of putting it makes the eternalist picture feel deterministic in a strong sense, and the determinism can be uncomfortable for those who place high value on freedom and agency. There is a partial response to this discomfort, which is that the eternalist picture does not actually require the kind of strong determinism that would eliminate choice. Quantum mechanics, as we have seen, introduces an element of probability that may complicate the simple block. The future may not be uniquely determined by the past, even within an eternalist framework. The structure may contain multiple branches, or it may have features that are genuinely indeterminate, depending on which interpretation of quantum mechanics one adopts. So the future being part of the block does not, by itself, mean that the future is fixed in every detail. It means that whatever the future turns out to be, that future is already part of the structure in whatever form it takes. There is another consideration that bears on the question of consciousness and time. The experience of being conscious involves a sense of continuity, a feeling that the self of this moment is the same as the self of a moment ago, and that this self will continue into the next moment. This continuity is one of the most striking features of consciousness, and it has been the subject of considerable philosophical analysis. In the eternalist picture, what is the basis of this continuity? If the self is a world line, then the continuity is built into the structure. The self of this moment and the self of the next moment are connected because they are adjacent points along the same world line, with all the memories, dispositions, and physical properties of the brain carrying over from one to the next. The continuity is a feature of how the world line is arranged in the block, not a feature of any flow of consciousness through time. But this raises a deeper puzzle. If all the moments along the world line exist together, why does consciousness experience them sequentially rather than all at once? Why does the version of you at one coordinate not have access to the experiences of the version at another coordinate? Why does each slice of the world line have its own contained experience, rather than the entire world line having a single experience that encompasses all of its moments? These questions probe the relationship between consciousness and the structure of spacetime in a particularly direct way, and they do not have settled answers. One possible response is that consciousness, by its nature, requires a certain kind of local integration. The experience at a particular moment is the result of the brain state at that moment, including all the neural activity, all the memories that are currently being accessed, all the perceptual inputs that are currently being processed. The experience does not extend beyond the moment because the integration does not extend beyond the moment. The brain at a different time coordinate has different contents, including different memories and different perceptions, and it gives rise to a different experience. The two experiences are connected by their position on the same world line, but they are not unified into a single experience because the integration that constitutes experience is local to a particular slice of the world line. This response treats consciousness as something that arises from the activity of the brain at a particular moment, and that does not extend beyond that moment in its felt character. It is consistent with the eternalist picture, but it does not fully explain why consciousness has this local character. There may be deeper reasons, having to do with the nature of subjective experience and the way it depends on physical processes that we do not yet understand. The relationship between the four-dimensional structure of the brain and the apparently temporal character of consciousness is one of the open frontiers in philosophy of mind, and it is one of the places where the eternalist picture connects most directly to questions about the nature of experience itself. The question of free will has haunted the eternalist picture from the moment it was first articulated, and it deserves careful examination. If all the events of your life are already part of the four-dimensional structure of the universe, then in what sense can you be said to choose any of them? The decisions you will make tomorrow are, in the block universe, already at their coordinates. The decisions you have made in the past are at theirs. Your world line, in its entirety, is a fixed feature of the structure. If you cannot alter it, then how can you be the author of any part of it? How can the things you do count as your choices rather than as the unfolding of a pattern that was always going to unfold in exactly that way? This is one of the oldest problems in philosophy, and it predates eternalism by thousands of years. Long before relativity, thinkers had wondered whether a world governed by deterministic laws could accommodate any meaningful sense of human freedom. The classical version of the problem assumes that the past determines the future through fixed causal chains and asks whether there is room within such a structure for genuine agency. The eternalist version of the problem is similar but more pointed. It does not just say that the future is determined by the past. It says that the future already exists in just as concrete a sense as the past does. The future is not waiting to be made by the choices of the present. It is already there, at its coordinates, complete. There are several responses to this challenge, and they correspond to different ways of thinking about what free will actually requires. The first response, often associated with the philosophical position called compatibilism, argues that free will, properly understood, is not the ability to do otherwise than you actually do. It is the ability to act according to your own desires and reasons without being coerced or constrained from outside. On this view, you can be free even in a fully determined universe, as long as your actions flow from your own deliberation rather than from external compulsion. The fact that your deliberation itself is part of a determined or fixed structure does not undermine its character as deliberation. It just means that deliberation is the kind of process that, given who you are and what your circumstances are, produces particular results. The compatibilist response has the virtue of being internally consistent. It explains how the experience of choice can be meaningful even within a deterministic or eternalist framework. When you deliberate about what to do, the deliberation is real. The weighing of options is real. The decision that emerges is real. These processes are part of your world line, part of the structure of the block, and they have their natural place in the chain of events that constitutes your life. The fact that the outcome is fixed in the structure does not mean that the process leading to it is unreal. It means that the process and the outcome are both part of the same structure, both equally there. A critic might object that this is not really freedom in the sense that matters. Real freedom, the critic might say, requires the genuine possibility of doing otherwise. If you could not have done other than you did, then you were not really choosing. You were just acting out a script. The compatibilist would respond that the question of whether you could have done otherwise depends on what you mean by could. If you mean that your world line could have been different, then no, your world line is what it is, fixed in the block. But if you mean that, given the kind of person you are and the situation you were in, you had the capacity to consider alternatives and to act on the one you preferred, then yes, you had that capacity. The capacity is part of what makes you the kind of being you are. The fact that the exercise of the capacity produced a particular result is just the consequence of the capacity meeting the situation, with the result being what the meeting produced. The second response is more radical. It argues that the eternalist picture does not require strict determinism in the first place. Quantum mechanics, as we have seen, introduces an element of probability that the classical block universe does not contain. If the universe is fundamentally indeterministic at the quantum level, then the future is not uniquely determined by the past, even within the structure of the block. The block contains everything that happens, but what happens is not fixed by what came before, in the strict sense that classical determinism would require. There is room for chance, for outcomes that could have been different, for events that are not strictly necessitated by their antecedents. This indeterminism might or might not be relevant to human choice. The decisions of conscious beings involve neural processes that operate at scales where quantum effects may or may not play a significant role. The question of whether quantum indeterminism affects mental events is a subject of ongoing debate, but the existence of quantum indeterminism at all means that the universe is not, in the simplest sense, fully determined. The third response abandons the question altogether. It argues that the concept of free will, as traditionally understood, may not be the right concept to apply to human action. Free will is sometimes defined in a way that requires an uncaused cause, a starting point of action that is not itself the result of prior events. This kind of free will, sometimes called libertarian free will, has always been problematic. It is hard to see how an uncaused cause could be coherent. If your choice is uncaused, then it is in some sense random, which does not seem like freedom either. The libertarian version of free will may be a conceptual confusion, and the right response may be to give it up. What remains is the practical reality of human action, the fact that we deliberate, decide, and act, with consequences that flow from our actions. This practical reality does not require the metaphysical baggage of libertarian free will. It just requires that human beings are the kind of beings who deliberate, decide, and act. The eternalist picture does not deny this. It contains it. These responses can be combined in various ways, and different thinkers favor different combinations. But they all share a recognition that the eternalist picture does not, by itself, eliminate the possibility of meaningful human action. It changes the metaphysical context in which such action occurs. It denies that the future is open in the sense of being undetermined or uncreated. But it does not deny that human beings act, choose, deliberate, and influence what happens. The actions are part of the structure. The choices are part of the structure. Their being part of the structure does not make them less real. It just means that they are real in a different way than the presentist picture would suggest. There is something to be said for sitting with this picture and letting it settle. The first reaction, for most people, is resistance. The idea that the future is already there, that one's choices are already made in some sense, feels oppressive. It feels like a denial of something important about being a person. But the resistance often softens with reflection. After all, the structure of the block contains your deliberation, your concern about your choices, your effort to act well, your attempts to influence the world for the better. These are all part of who you are. They are not negated by being part of the structure. They are constituted by being part of the structure. The picture does not say that nothing matters because everything is fixed. It says that what matters is part of the structure of reality. Your love for your family is part of the structure. Your work to improve your life is part of the structure. Your striving to be a good person is part of the structure. These things are real because they are in the structure. The structure being fixed does not make them unreal. It makes them permanent. This shift in perspective is worth dwelling on. In the presentist picture, the things that matter to you are passing. Your love exists now, but will be gone. Your accomplishments exist now, but will fade. Your moments of joy exist now, but will not last. The whole of life, from this perspective, is a kind of slow loss. Everything that you care about is on its way to non-existence, and the most you can do is enjoy it while it is here. In the eternalist picture, the things that matter to you are permanent. Your love exists at its coordinates and will always have existed. Your accomplishments exist at theirs and will always have been accomplished. Your moments of joy are not slipping away. They are part of the four-dimensional structure of the universe, fixed in their place, unchanging. The whole of life, from this perspective, is not a slow loss, but a definite contribution to the structure of reality. Whatever you build in the deepest sense into the permanent fabric of what exists. This is a different way of relating to one's life, and it has been a source of meditation for those who have taken the eternalist picture seriously. It is not exactly a religious view, but it has some of the same features that religious views provide. It offers a kind of permanence to the contents of life, a sense that what one does and experiences is not erased by time, but added to a structure that endures. It offers a different way of facing mortality, in which the end of life is not the annihilation of everything that has gone before, but the boundary of a complete existence, with all of its contents preserved in the structure of the universe. Whether these consolations are warranted depends on whether the eternalist picture is correct and on what one makes of the relationship between the picture and one's own life. But they are at least available in a way that the presentist picture does not make available. There is another aspect of the free will question that deserves mention. The eternalist picture, by treating all moments as equally real, places the present in a particular relationship with the future. The future, in this view, is not waiting to be brought into being by the present. It is already there. Your actions in the present do not create the future. They are part of the structure that includes both the present and the future, with the relations among them already set. This sounds like a denial of efficacy, but it need not be. Your actions in the present are still causally connected to the events that follow them. The connection is part of the structure. The events that follow your actions follow them because of what those actions are. If your actions had been different, the subsequent events would have been different. The structure includes the causal relations among events. The fact that the structure is fixed does not eliminate those relations. It contains them. What it eliminates is the picture of the future as a region of possibility that gets narrowed down to actuality by present choices. In the eternalist picture, The future is not a region of possibility. It is a region of the block, just as the past is. What you do now is not the act of selecting one future from among many possible futures. It is the act of being the kind of person you are, doing the things you do with the consequences that follow. The future that results is the one that results. The other possible futures are not waiting somewhere, ready to be selected if you had chosen differently. They are not part of the structure at all. Only the one future, the one that actually occurs, is part of the structure. This is a hard idea to fully internalize, and it requires letting go of some of the most basic assumptions we make about how time and choice relate. But it is the picture that the eternalist framework demands, and it raises further questions, including questions about whether there are, in some sense, multiple realities, multiple branches of the block, multiple ways the structure could have been or might be. To address these questions, we need to consider the possibility that the universe contains not just one history, but many.